Welcome, everyone. In this session, we're going to walk through an advanced mediation route that applies more complex enterprise integration patterns from Apache Camel. We're going to focus on the enricher, splitter, and multicast EIPs. These will give us an opportunity to examine some more advanced Camel concepts like logical endpoints with their own staged event-driven architecture thread pools. Applying multi-threading is a key concept for scalable, asynchronous, message-based integration. When using the enricher, the splitter, or the multicast components in Camel, you have the option of applying an aggregation strategy. So we're going to see how that is applied as well. Finally, as we pass messages around with multiple exchanges in multiple threads between Camel consumers and eventually to Camel producers, we have to pay special attention to Camel message headers and how we manage them. So we're also going to see some common best practices for managing headers with namespaces. Here are the primary EIPs that we're going to be using, as well as the URLs where their documentation describes their APIs. All of these are available on the Apache Camel site, as well as help.talend.com, and they can also be found in PDF format in our documentation downloads. So let's drill down into the actual service that we're going to be implementing. We're going to implement a composite service that makes use of the ARIN Whois capability. ARIN is the American Registry for Internet Numbers, and they expose a RESTful API for the traditional Internet Whois capability. Like a good REST API, it is resource-centric, focusing on resources like network blocks, IP addresses, and organizations. We're going to walk this resource hyperlink web using the ARIN API in the following manner. We're going to start with an arbitrary IP address. When we query it, we'll see that we get potentially multiple network blocks. We're going to drill into each network block and identify the starting address. And for that starting address, we are going to find the first 10 IP addresses and ping them. We're going to aggregate the results of the ping for that network block and then roll those up again for each network block in the aggregate set of network blocks, plural. In addition to those ping results for the network blocks, we're also going to navigate to the parent organization. We're going to do that in a manner that is RESTful. So we're not going to take advantage of any of the naming conventions from ARIN to kind of parse the URL and figure out what the org URL should be. Instead, we're going to use this reference link in the actual payload and then invoke the other service with an HTTP GET call. Once we get those results, we're going to parse them and extract out information about the organization, such as its handle and its address. And here's what that will look like. Here's the URL from the previous example. And when I query that, you can see that it's got the country with its ISO code, it's got a handle, it's got a name, it's got a postal code, and a street address. We're going to grab all of that, and we're going to mash that up with the previous results of the pings, and then we're going to send that back to the client. And the client could be a browser client making a RESTful API call. In that case, we might send back either JSON or XML. But we're also going to expose the same service at the same time as a SOAP endpoint. And in addition, we're also going to expose it as a JMS endpoint. So we'll see how all three of these access points can run concurrently against the same logical endpoint that actually implements our composite service. So let's drill down onto how we're actually going to do this in the Camel routes with Talend Studio. So, don't be too scared by the size of this route. Each of the individual steps are very simple. There's not a lot of complex procedural Java code here. Instead, we can take advantage of the visual drag and drop metaphor and configuration rather than code through the properties of these EIPs and Camel endpoints. So let's start with the RESTful approach. Here we have the REST endpoint that we're going to expose, and we're exposing it at this URL. And this URL uses externalized parameters, which we call context properties. So these can be changed at runtime by the operator and then injected into the route. So if we need to change these properties, it's easy. But the bottom line is we're exposing it as a URL, and we have this match on URI prefix so that whatever IP address is appended, the message is still going to get routed here. Once it's routed here, we're going to extract the HTTP accept header. Now, fortunately for us, Camel will automatically map the HTTP header into the Camel message, and then we can use Camel's simple language to access that with just header.accept in this case. So we're going to get that header, and we're going to store it away somewhere safe in the exchange as an exchange property with the set property command, and we're going to call it the same thing. And the reason we're going to do that is we want to put it somewhere safe in the exchange, because later on we're going to see that we need to clear out the headers. Because as nice as it is that Camel maps those HTTP headers into the Camel message for us, later on when we send that message out with a Camel producer that creates a new message that is sent to the external world, Camel will do the same things with those headers, and we may not want those headers to interfere with downstream Camel producers, and we may not want that data to be exposed accidentally to the external world. So we're going to clear out the headers before we send them. But if we clear out those headers, then we're going to lose this information. So we're going to take the information we're interested in, store it in an exchange property, and then we're safe. So after we log it, then we also want to extract some information from the URL of the HTTP request itself. And for that, again, Camel helps us out by automatically mapping the request URL to this well-known Camel message header called exchange.http path. So we're going to take that, and we're going to parse that for the last segment of the URL, which is the IP address. And then this time, we're going to take the IP address and stuff it into the actual message body, because that's really the payload that constitutes the parameters for our internal service. Now we're ready to go. So we're going to send this to the content enricher. And the reason we're sending it to the content enricher rather than just sending it directly is because we want to preserve our original exchange. And we're going to create a new exchange with new headers that we're free to clear out ourselves. And here is the content enricher, and it's specified that we're going to send the message, or actually create a new exchange to the VM:/enrichWhois endpoint. That's this one here, enrichWhois. And the VM protocol in Camel is an internal in-memory protocol to a staged event-driven architecture endpoint. And all that means is it's a logical endpoint with its own thread pool and its own message queue. Now, in this case, we said we're only going to have one consumer. That's just for example purposes. We don't really need more than one. But we could set this to 10 or any other number, and we could even externalize this as a context property so that the operations team could set it if they chose. Once we receive that message on our CETA queue, we're going to clear out those headers like we said. But we're going to keep two headers, the correlation ID and the coordination ID. And that just says, hey, if there are these special headers, we're going to remove everything specified that matches the first parameter except those headers that match the second, third, or any other parameters. And now we're ready to invoke the actual logic of our service. We route it to the whois direct endpoint, which is this one here. We log it, and then we're going to set some headers in the message itself. We want to set these well-known headers called the HTTP path with the IP address that we parsed from the message. And recall that we stuff that into the body of the message. So that's what we're doing here. Then we send it to the Camel producer, who's going to invoke the ARIN REST service for that IP address. When we get the results back, we're going to convert them to a string, and then we're going to use more XPath expressions to parse the results. Notice that the ARIN request did use namespaces, so we must respect those. Let's take a look at that again. Here's the ARIN RESTful service, and if we query it, we see here are these namespaces, www.arin.net/whoisrws. So we have to respect that by declaring those same namespaces having a prefix here. The prefix doesn't have to match their prefix, but it does have to match the actual URI, and we specify that in our XPath. What we're extracting is the organization, the network, and the network reference. Having extracted that safely to our headers, we can now send these results to the two segments that we want to execute in parallel. As you recall, we want to ping a bunch of addresses, and in parallel with that, we want to query ARIN about additional organizational details. So let's start with the second one because that's a bit shorter. The multicast specifies two logical endpoint targets. The second one is named query.org, and that's this one here. This time, we do have a number of concurrent consumers, and we also have a maximum queue size. So while these threads are constantly consuming messages, they can support a backlog of unprocessed messages. But if that backlog becomes larger than, say, 6, which we've configured, then it's going to throw an error. It's not going to accept that message, and the calling thread that tried to put the message onto the CETA queue will immediately get an exception, which it can then process as it sees fit. So with that staged event-driven endpoint, we are then going to remove the headers again, but this time, notice that we have an additional exception. We're going to clear out all the headers that match this regex pattern, with the exception of those called correlation ID, coordination ID, and also those that follow the pattern of ARIN.wildcard. And as you may recall, those are exactly what we extracted in the previous step. We followed a naming convention and applied a namespace to our Camel headers so that we can manage them. The reason we need those is because in the next step, we're using the arin.org header as part of our URL so that we use another Camel HTTP endpoint to invoke the ARIN.org resource. We get the result back, we convert it to a string, and then more XPath, also respecting the ARIN namespace, to read the organization handle, name, city, state, and zip. So far, so good. Having gotten all of that information, we want to embed that into an XML result payload that follows our own internal schema. And we can do that by using a simple string as the template, and then wherever we need values, using the Camel simple language, which is very easy. You can see the $ with the curly Q brackets, and wherever we have a header, we just say header.headerName. So with this, we represent our organizational details, and they return the results to the multicast element. Now that's great, except that we still have all of the ping statements to do. So, as you recall, multicast was also sending those same messages to the netblocks element here. And if we go back to the original ARIN request, we can see that there was netblocks plural. We happen to only have one here, but we could have more. So what we want to do is split all of these results on the XPath that says /net, /netblocks, /netblock. So we're going to take in one single message, and we're going to get out multiple messages using that splitter XPath expression. When we do that splitter expression, we need to respect the ARIN namespaces. And for each of the multiple outbound messages, we're going to send it down this purple route, the split route, to the VM process netblock endpoint. That endpoint has multiple consumers. So it has a thread pool of listeners waiting to process one thread per netblock call. Once it receives a netblock, it's going to extract out the starting IP address using XPath again, and then we're going to create a string of the first 10 IP addresses separated by commas, because we can, again, split that with the standard tokenizer, and the splitter will respect the same route path for the tokenizer. So we had one string of 10 comma-separated IP addresses, one string payload going in with 10 individual messages going out on the purple route. They all go to this ping address here, because this ping corresponds to this ping endpoint where we have 5 listeners. In this case, we have a queue size of 20 because we might expect some of these to back up because ping can take a while to run. And then we invoke the system ping command. We capture the output stream of the ping command, and that's what we're going to return. When we return it to the splitter is going to apply this aggregation strategy. And the aggregation strategy we've defined is very simple. It is an append aggregation strategy that just takes the new result and appends it to any previous results. And it sends it to the next step along this red route. So the purple route is the splitter route, and the red route is for the aggregated results. So one message in on the red line, many messages out on the purple line, aggregation, and then one message outbound on the other red line. So once we've aggregated all the ping results, we want to wrap them with some additional XML that's consistent with our internal schema. Then we're done with the ping results. They return to the splitter that invoked this message, which was the netblock element. Now, we only had one netblock in our example, but there could be more. So we again wrap that in a netblock element. Very simple, the same kind of Camel simple template with the individual header results. This returns to the multicast element. The multicast element also has an append aggregator. So this time, however, it's appending all of those netblock ping results with the results from the organizational query. So we want to wrap that with the whois response wrapper. And again, we want to respect whatever schema we specified. And that schema in the REST case, doesn't really have a representation because there's no WSDL in this case. But it does have a representation in our SOAP endpoint, and that's the schema that we're trying to respect. So after we've wrapped that in a way that's consistent with that XML, this route here is done. It goes back to the enricher, which is also done. And sure enough, it returns to the content enricher in the REST endpoint. The next step is to format that output. Many times when we invoke this REST service, the browser will be requesting XML. But some of the time, the browser client may request JSON. And if it does that, we're going to route the message to this logical endpoint, which will use a content-based router based on that accept property that we saved way back here. We saved it in an exchange property that loaded it from the HTTP header that was itself loaded into a Camel header. So if the client browser specified application/JSON, then we're going to use this one-line statement to marshal the data from XML to JSON. We don't have to do anything. We don't have to write any procedural Java code. We don't even have to create a transformation with a visual tool. It's all done for us. And then we're done. So only if the client-specified application JSON will this be applied, because it's in a conditional content-based router. If that was not the case, then it returns immediately. Now we have the marshaled result, which we are going to send back to the client. And that's it for the REST endpoint access to this common logical service. But we know we have two other access points as well. But they're very similar because they reuse the same unified interface based on the standard Camel headers. So let's look at the SOAP endpoint. It looks very similar. We, this time, have a slightly different URL and port, and we have a WSDL. But other than that, we log the request. We get the IP address this time from the payload of the SOAP request. We didn't even bother to bind the SOAP request. We just specified payload mode because it's very easy to parse the payload. Then we send it to the same route that the REST request did. When we get the result back, we don't need to send it to the data formatter. The only thing we do need is to add one additional wrapper layer to respect the semantics of the doc literal style for SOAP. Then we get to return the result and we're done. Now JMS is similar, except JMS has a little bit more flexibility. With the REST and the SOAP endpoints, they default to the in-out message exchange pattern. When these routes get to the end, the in-out message exchange map says return the final result back to the starting endpoint and then send that back to the client. Same thing for SOAP in this case. JMS could be either in-out or in-only, and it depends on whether the sender of the JMS message sent a reply to header. So in this case, we're going to do that by convention, and we'll see that when we invoke it. And we're also going to observe an arbitrary convention of using JMS user properties, and if those properties have an accept property that's mapped that happens to be named accept, we're going to apply the same data format rules. Everything else is the same. We log it, we convert the JMS message to a string, and we send it this time directly down here to the whois message. The only reason we're doing that is to see what happens when you ignore the cautionary tale of removing headers. But this will work just fine in this case. So we've exposed our common service with 3 different access points, and let's see it in action. Let's start with the RESTful service. Here is our query. Oh, might be a good idea if we actually started our service. Now, we've already started ActiveMQ in the background, but just in case, that was configured here, that connection was configured via the JMS endpoint. Everything is started, so let's start with our ARIN IP query. We're exposing it on port 9011. Here's an arbitrary IP address, and notice that we have set the accept header to be JSON. So when we send this, we see that it's running, and right away the organizational part of this is finished. But what's taking a long time is the ping part of that. And you're only seeing some of the pings go through in a batch because we have to do 10 pings, but our pool was only a size 5. So it takes at least 2 passes. Now everything's done. We see 10 down here. And sure enough, here's our output all the ping results. Here's the org result, and it's got curly Q brackets because it's JSON. Suppose instead we had said XML. We send the request, and we have some time here. Let's observe that we started at 10, and it's going to get to 20, but a lot of these are still waiting on those timeout pings. Those are the ones that take a long time. Now, eventually, we have one more to go. As soon as that gets to 20, the aggregator will be done, and it will pass it back up the chain. Looks like that last one took a while. Oh, there it goes, finished at last. And sure enough, here's our output this time with XML. Let's do that with SOAP. Here is the URL for our WSDL, and I'm using Chrome here, so we've got this handy little Chrome extension that allows me to invoke the ping operator in this other tab. It pulled up the WSDL payload, kind of like SOAP UI, but it's easier, quicker. And I've put the same IP address in, so when I click Go, it's loading, meaning it's running, and I can see that the message this time came down the SOAP pathway. And again, the organizational query is finished. It's the third query we've done, but this one's still running, and it needs to get up to 30. And there it goes, 30. So sure enough, I'm back in the browser, and it's done. And this time it's XML, slightly different. It's got a SOAP header. It's got the SOAP body. And here's that extra layer from the doc literal style wrapper called ping response. And that's based on our WSDL. One last example. Here's JMS. We were listening on the Aaron.whois header, and you can see that. I'm going to refresh this. You can see that we've got 3 consumers listening on this whois queue. I'm going to send a message to that, and the message that I'm going to send is just the IP address. And I also am going to fill in the reply to address. And I'm just going to call it Aaron.reply. So when I send this message, you can see it's still in the queue, actually. And that's because this is, a JMS transaction, and it hasn't finished yet. We've read it here, but it's still executing. The organization is done, and this one's almost done. It's on 35 of 40. So once it gets to 40, everything's going to finish, and then the JMS transaction will finish, and then we'll have a result. And looking down here, that's it. 40 is done. The JMS is now done. I go back to the browser. If I do a refresh, Aaron.whois is finished. The message has been dequeued. Here's our reply. If I look at it, sure enough, here's that same XML payload as we saw in the REST and SOAP examples. It does not have the response wrapper because it doesn't need that because it's not SOAP. Notice also these JMS properties. In this case, we didn't pass it through the enricher stage. We did not remove all those other headers. And whoops, we are accidentally advertising potentially all this other header information that if we weren't diligent about, this could happen. It's usually not an issue, but it's always good to be a defensive programmer. So in summary, what we've seen in this example is use of various components like the enricher, the splitter, and multicast EIPs, all of which offer multi-threaded behavior, which are configured with an aggregator. And it's important to understand that for the splitter and the multicast element, you get one message in, many messages going down the purple route to the targets, which can be in parallel if you click on the parallel checkbox here. One message in, many messages being split. After they're aggregated, one message going out on the red line. So that's it for this session. I hope it's been useful. You can find more documentation and more information on help.talend.com and our partner portal as well. Thank you for your time.